here's the good news and the bad news. The good news is you now know everything you need to know about statistics, because so much of what happens in statistics is what we've just been going over, the null hypothesis statistical test paradigm. And you've got the framework for it. And now everything you're going to encounter is always brought back. Well, I shouldn't say everything, but a huge amount of what happens in modern statistics is brought back to this framework. Now, what gets tricky is everything gets brought back to the same framework, but things are done just a little bit different each time. And what we're going to do now is for the last parts of the term, we're going to introduce two more authentic tests that you'll encounter. Because in truth, in reality, there aren't many research questions where you're asking, is this population average a given number? More often than not, you're actually comparing two groups and asking if there's a difference between the groups. So that's what we're going to focus on in the last two parts. So what I'm going to do is I'm going to give you, this actually is authentic data. It is, I will tell you, it is a curious finding because it's a subset of a larger data set. And in the larger data set, the finding that we're going to see here is not what the researchers found. Well, actually, it is what the researchers found and they published it, but then when they looked at the larger data set, they realized, this just happened to be a chance occurrence. But let's go ahead and walk through this. So we're going to talk, so again, which is what are called matched pairs t-tests. Okay, and again, this is a null hypothesis statistical test, so we will see that framework, but there's going to be slight little variations in how we do things in this. All right, so let me go ahead. I'm actually just going to go ahead and give you the claim. So the claim for this is the following. Okay, so you've all probably heard something along the lines of ERs always have more happening. There's always more people coming into the ER on a Friday the 13th or on a full moon. And so what we have here is the following data. So let me go ahead and give you the data. I can actually type it out. It's not a tremendously large amount of data. So I can go ahead and type it here. So what we have, what the researchers did is they collected data on Friday the 13th, but they also said, well, let's compare. So if there's something special about Friday the 13th, let's compare it to the next best thing, which would be Friday the 6th, which is the Friday right before a Friday the 13th. And so what they had is they observed the following. They counted how many particular types of accidents showed up in the ER that they were monitoring on the Friday the 13th. I think they were actually just counting the number of people that came in with broken bones. I believe that's what it was. I can't recall exactly because it's been a while since I've actually looked at the research for this problem, but I think that's what it is. So what they did is they kind of, obviously you kind of had to go over a couple of years because not every month has a Friday the 13th in it, okay? So they had to go ahead and collect the months that had this data. And here were the months that they found that had a Friday the 13th. So in those months, they looked at the ER records and determined that, so for the first row here, it means on this month, there were 9 people that showed up with broken bones on the 6th, but there were 13 people that showed up on the 13th. So here we have our claim. Here we have our data. So what we want to do is we need to write out the null hypotheses for this, okay? And here's where things get a little interesting because if I'm claiming that there's more accidents on Friday the 13th, let's let mu be the mean of the number of broken bones on this day of the month. All right, so if I wrote the following, mu sub 6 and mu sub 13, do you see how I'm talking about two different averages here? Mu sub 6 is the average number of broken bones in the ER on Friday the 6th, and mu sub 13 is the average number of broken bones on Friday the 13th. For my claim, what should be the relationship of these values according to my claim? And I'll put it in orange. What relationship symbol should I put between there? If there are more accidents on one day versus another, what symbol should we put in there? Less than? How do people feel? Do people feel comfortable if we put that in there? This essentially says that whatever the average is on the 13th, it is going to be bigger than the average on the 6th. I think that's a reasonable assessment. So again, this is a strict inequality, so this indeed becomes the alternative hypothesis. Now, there was an observation that we're actually going to turn this into a subtraction, which we will here in just a second, because we kind of have to be able to draw a curve. But the opposite of this would be that the average on the 6th would actually be greater than or equal to what we actually observe on the 13th. All right, now again, I want to emphasize this is what we call a matched pairs, or what's called a repeated measures test. Okay, and it's called a t-test because we're going to use the t-test statistic. We're going to use a t-ratio to solve this or to understand this. So what I need to do now is I kind of need to show you like 1,010 ways to write the same thing. All right, so bear with me here. So what we're going to do is I'm going to take these hypotheses. I'm going to take these hypotheses and we're going to play around with them just for a little bit. And you'll see why in a moment why this is an important thing. But bear with me for a second here. All right, so let me go ahead and clear. If everyone's good with this, I'm going to go ahead and clear the screen here. All right, I'm going to go ahead and rewrite these hypotheses. So, try that again. So the null hypothesis is, that as I've written it, the null hypothesis was that mu sub 6, or the average on Friday the 6th, is greater than or equal to the average on the 13th. Okay. So what I'm going to do now is I'm going to rewrite this in the exact same way, but it's going to say the same thing, but it's going to look different. So I could have rewritten it this way as well. This says the exact same thing, doesn't it? The average on the 13th is less than or equal to the average on the 6th. Okay. And I could have also done this. I could have said the average on the 13th minus the average on the 6th is less than or equal to 0. Okay. Or, and this is the notation that we see a lot, I could also write that the average of the difference, and we use capital letter D in the Greek symbol, the Greek notation, that's called the letter delta. So the average difference for the pairs is 0. All 4 of these are saying the exact same thing. All 4 of these are saying the exact same thing. So the corresponding alternative hypotheses would be that mu sub 6 is less than mu sub 13, or in this notation, mu sub 13 is greater than mu sub 6. Or if I were to subtract these values, the average of mu sub 13 minus mu sub 6 would be greater than 0. Or the difference, the average of the difference would be greater than 0. So all 4 of these actually say the same thing. Now, note if I had done my subtraction over here, if I had done it mu sub 6 minus mu sub 13, then this notation would actually be reversed. That is really, really important to note. So let me just kind of make an observation here. The direction of the subtraction, I can spell subtraction, determines the sign for mu sub delta. So if I had done the subtraction, of mu sub 6 minus mu sub 13, this sign would actually, the notation would be the same, but this sign would be going the other way. Now, unfortunately, a consequence of that is that when you do these tests, a consequence of this is that when you do the tests, what ends up happening is that you actually can have the signs going in both directions. So you could do it one way and get a positive value, and you could do it the other way and you get a negative value. So that's why you sort of have to be very careful. You have to keep track of the analyses that we're actually using here. I think for what I'm going forward, I'll continue with this notation here. So where the average, I hypothesize that the average difference is going to be greater than 0 because I'm subtracting the 6th from the 13th. This handout is available in the dark green folder, the handouts folder of the current module. All right, so hopefully everybody can see so this is the template that I prepared for you. And this template is pretty much the template that you can use now for you can use this for any matched pairs t-test. Right. So let me walk you through what's in here and then we'll connect it to the setup that we've been working with. So you notice I've typed in the data here for the 6th in column A. I've also sort of given a little label up here so I can keep track of it. I've done the same thing in column B. And what I've done here is I've just emphasized the order of subtraction. I'm subtracting column B. I'm taking column B and then subtracting column A. If you notice in the formulas over here, each of these values is this value minus this value. And then I just copy that down. So if you have more columns, then more rows in your data, you would just copy down even further. Okay? But now all that I'm going to focus on now is, so here we have the information that we started with, but in truth, we're actually working with only one data set. So what we say in this context is we say that the data requires a transformation. That transformation here is what we've seen here. So this is the transformation. We essentially taken the values and taken two paired values and converted them into just one value. So now if I focus only on this, let me see if I can highlight this. I didn't think I could. So if I focus only on this part of my picture, so if I focus only here, what I have now is I no longer have what appear to be two data sets, but now I really only have one data set. So each person had two data points, but I've transformed the data so it's all been rewritten. So now there's only one quote unquote observation for each person, or in this case for each calendar month in which there's a Friday the 13th. So in this month, there were 4 more broken bones in the ER on the 13th than there were on the 6th. In this month, there were 1 fewer. What we do here is we take the average of this column, and I take the standard deviation of this column, and I get to count. There's 6 values. And my formulas work exactly as they did before. I'm going to take my average from my hypothesized value. But remember, what actually is my hypothesized difference here? What was mu sub d? What did we hypothesize that value to actually be? Go back and look at that really quickly. What did we say that value was? What did the null hypothesis give for that? The null was that it was less than or equal to 0. Exactly right. So this is less than or equal to 0. So when I draw my curve, I have to draw it at the value 0. So essentially, I'm just going to write it. The null hypothesis is this, but I'm actually going to write it this way. So if I take my observed average difference and I just subtract 0, that's subtracting 0 doesn't really do anything. So I'm quite literally just going to take this value and divide it by the standard error. The standard error is calculated the same way. I get the standard deviation of my differences, divide by the square root of the sample size, and that gives me the standard error. So this value here, this is my t-test. That's the t-ratio. Using the TDIST function, I can find out what the probability of this happening is, and I'm going to walk you through what this formula is here in a second. I'm going to give, so this is 2 different versions of the same this is 2 different versions of the same analysis. I'm going to explain what this actually is. The problem is that my test, the test that I was asking for was a one-tailed test, and this is actually a 2-tailed value. So remember, we actually, that's not an issue. If we need to go back and forth between those, that's actually not a problem. We can do that. The one-tailed p-value equals the 2-tailed p-value divided by 2. So we can just divide those and we'll get the value. So that's how we convert. So this right here is a 2-tailed p-value. And how do I know it's a 2-tailed p-value? Well, it's actually, let me show you. I know it's 2-tailed because of this. So this here is what tells me it's a 2-tailed p-value. Okay, so that's what tells me it's a 2-tailed p-value. All right, so let's take this information and summarize this now. Okay, so again, I'm going to focus on this piece of information here. So let me go ahead and erase the rest of this. So again, this was our null hypothesis. So if I draw a sketch of this, it would look like this. Okay, my average difference is centered at 0. Now, if I believe the average difference is anything that is, if I believe the average difference, it could be less than or equal to 0, I wouldn't be surprised by values down here. I would only be surprised by values up here. So this is an example of a right-tailed test. And again, if I set my significance level at 0.05, I can set it to any reasonable value I want, but it's arbitrary. I get to pick it, but I do have to state it. Now, remember, my t-ratio that I obtained from the output, if you go back and look at it, it was t equals 2.7116, p-value for that it came out to be 0.0211. And we notice that that is indeed less than our given alpha, which implies that we would reject the null. So putting this all together, the sample data support the claim. Okay, so that is the restatement of our claim for this statistical test. Sample data support the claim that more accidents happen on Friday the 13th compared to Friday the 6th of the same month. So let me go back and show you one other bit of the code, because I kind of skipped over this. So Excel has, so one of the things that we've been doing in class is sort of building up these Excel templates that we can use, but Excel actually has more advanced functions built in. And one of those functions is this TDIST function. Excuse me, the T.TEST function. So we've been talking about the TDIST function. So that's the function that we've been focusing on. What I'd like to focus on now is the T.TEST function. This is a different test. This is a different function in Excel. And in this function, we have to give it 4 things. All right, so I'm going to highlight each of these 4 things in turn. All right, so the first thing we have is the first column of data. And then we have the second column of data. So this is that's the second column of data. So that's the first column of data, and here is the first column of data is here. Oh, that didn't change colors. Try that again. There we go. Okay. Now, this 2 that we saw earlier, this 2 is this 2 that we saw up here is the same 2 as this one, okay? This is the number of tails in the t-test. So we can change that to be a one-tailed. So then the question then becomes, well, wait a minute then, what is this 1? So then the question then becomes, what is this 1 then? So the question is, what is the 1 that's highlighted here? Well, the 1 is what tells Excel that we are actually doing a matched pairs t-test. Okay, so this is what tells Excel which type of test we actually want to run. Now, again, remember, there's different types of tests that we're going to encounter. There's different types of tests that we can actually encounter. So this is the matched pairs test. The other test that we're going to see is the independent samples t-test, of which there's different versions of that. So in this case, so believe it or not, everything that we've done here, none of this is necessary, because if I have just the first column of data and the second column of data, I can just use the t-test function, and that will give me the p-value right away. So this jumps us directly to the p-value. And here's the moral of the story. This is one of those things that they don't tell you in statistics class. Well, actually, in my face-to-face classes, I always joke about this very early on, but everything in this course comes down to one number, the p-value, because in the end, the p-value is what we use to make our decision. There's a lot of machinery that's behind it, and you have to understand that machinery and understand how to interpret the results. But when it is all said and done, it is all about the p-value. It's just about that one single number, okay? So every statistical test comes back to calculating that number. So in this case, that's why this function is written this way. The function is written to just give you that one piece of information you need to ask if these values are actually different from each other. All right, so what I'd like to do now is I'd like to talk about the effect size, because in the effect size, I need something for the effect size. When I'm calculating the effect size, I don't need to use the standard error. That's used for the t ratio. What I need for the effect size is I need this standard deviation. Okay, this is needed for the effect size. Okay, so that value is needed for the effect size. So we'll need to take note of that. Right? But I also need to know what the average difference is, which in this case was 3 1/3. And what we'll do now is we'll actually calculate the effect size for this test. Okay, I'm going to leave this here because that's kind of important. So let's talk now about the effect size. So the formula for the effect size in this context is D equals the average difference for each of our observations divided by the standard deviation of all of the differences, the transform data. Okay, now this turns out to be, because these are paired, this turns out to be the average of the differences divided by the standard deviation of those differences. For our example, this was 3.33 and change divided by 3.0111, and that's an effect size of 1.11, which simply put, if we compare that to the what Cohen suggested, this is greater than 0.8. So that would suggest that this is a large statistical effect. Now again, remember, the effect size is sort of meant to be like a percentage. We know how to interpret percentages. I know what I mean when you say 20% of something. I don't know what a difference of 3.3 1/3 is in this context, but I know what it means for it to be 1.1 standard deviations. Okay, so that's why we say that we have an effect size here. That's how we use the effect size. It's that standardization. All right, so let's kind of do a summary and talk about some of the key assumptions. So when do you do what we just demonstrated here? So again, this design is called a matched pairs t-test, and the key is to be able to do this. For this to work, you must be able to actually make a pair. Okay, so for the matched pairs t-test, you must be able to actually pair your data. Okay, so when can you do that? Well, a couple common situations where that happens is if you have, for example, you sometimes have pre-test versus post-test data. Sometimes you have information on paired individuals like twins or spouses. Okay, our example was comparing. We were looking at 2 days from the same month. That was the scenario we just talked about. The point in all of these is that we were able to pair our data up in some commonsensical way where it made sense to actually pair the data. Okay. Again, the other term that's often used for this is it's called a repeated measures design, and so repeated measures is good when we're talking about something like post-test and pre-test. That's an example of repeated measures. Whereas twins or spouses, that's an example of collecting, or also using the 2 days from the same month would be an example of repeated measures. Twins and spouses are sort of collecting information from individuals. And they're distinct individuals, and they're only connected with each other because of the relationship that twins have or the relationship that spouses have. Now, the term matched pairs actually has a bit of history with it. The idea of a matched pair is sometimes you can't match people up. Sometimes you can't use the same person for an experiment, because once you've sort of done the experiment on them, you can't undo the treatment. So what we do in a true matched pairs design is we say, I'm going to find 10 people from the population chosen randomly, and then I'm going to do my best on some set of measures that I think are important, like gender, age, socioeconomic status, education, whatever those values are. I'm going to try to find another set of people in the population that match the criteria that I found for the people in my study. It's one of those guilty pleasures. Does anybody watch Bull, that quote unquote jury science? And I'm using really big air quotes when I say it. Nope. Nobody watches. Either no one watches or no one's willing to admit they watch. On that show, they make a point about when they quote unquote select their jury, they do their best to try to quote unquote find a person from the general population that they pay to sit in and watch the trial. And they say they've matched them so that they're essentially a perfect match. Well, the truth is that's impossible, but that's the general idea. So that's what we mean when we say matched pairs. Okay, so now there's a couple assumptions that come into play. So let's talk really briefly about the assumptions. So when can we actually do a matched pairs t-test? Because that's kind of the important part for this. When can we actually do this? So yes, you must be able to pair your data, but there's a number of other assumptions that have to be met as well. Okay, those assumptions are, first of all, you actually have to have what we call independent samples. And we mean they have to be independent between between the samples. So in other words, so if I were looking at the rows need to be independent from each other, because we obviously know that there's a lack of independence between each observations in the same row, because they're either from like the same twins, the same spouse, or they're pre-test, post-test from the same individual. And then the second requirement is that the differences are normally distributed. Now, emphasis that remember, the differences, that's the transformed data. So the curious part about this is your original data, your 2 columns, don't actually have to be normally distributed. Your 2 columns don't have to be normally distributed. What is required is that your the differences though have to be normally distributed. So let me go back to the handout just to reiterate that. So these columns here do not need to be normally distributed. But when I take the difference of these, this data, this does need to be normally distributed. So as long as as long as these differences are normally distributed and these values are all independent from each other, then you can actually do a matched pairs t-test. Relatively speaking, that's a fair amount of stuff that we've covered. But the truth is, we've covered a lot in advance to this to sort of set the stage so we could go through this. I don't want to say we've gone through it quickly because we've been talking about it for about an hour now. But this is the heart of what an authentic t-test would actually look like. And now let me summarize what we did. So for this one, recall our p-value was, so for the scenario we just walked through, the p-value was 0.0211, which we said was less than alpha equals 0.05. The implication here was that we rejected the null. And I'll just reiterate what the null was. The null said that the average difference was less than or equal to 0. And the consequence of this was that the sample data support the claim that more accidents happen on Friday the 13th. Okay, so that was the general gist. Okay. So here's my question for you. Here's end of class question number 1. Okay, that's the end of class question. If this conclusion is wrong, in other words, if this result over here is wrong, what type of error did we make? If this conclusion is wrong, what type of error did we make? A type 1 or type 2 error, and why? Why is it a type 1 or type 2 error? All right, so that's end of class question number 1. And we'll take a little bit of writing to do. Okay. End of class question number 2. End of class question number 2 is a little easier, I think, in some ways. So the next end of class question is, so this end of class question was specific to our problem that we just did, the Friday the 13th example. The next end of class question is a more general problem, but it's focusing on the other types of comparisons we can make with different groups. So here we have group number 1, and in group number 1 I have the following. So this is what we call the control group, and the scores from the people in the control group were as follows. All right, so those are my scores for the people in the control group. And then I have another group that were randomly assigned to the treatment group. And in the treatment group, here are the scores of the people in the treatment group. Okay, so here are the scores of the people in the treatment group. All right, so simply put, I'd like you to tell me, why do you know, so the end of class question is, this is end of class question number 2. So why do we know this is not a matched pairs design? In other words, why do we know that we cannot do a matched pairs t-test on this? All right, so 2 end of class questions there. Not usually what I do, but the timing and the spacing of this didn't work so well otherwise. So those are the end of class questions.